Hello, my name is Cameron Bernado, and today we will be discussing Pascal's triangle. Even though Pascal's triangle received its name from the 17th century mathematician Blaise Pascal, numerous other mathematicians were aware and applied their knowledge of the triangle centuries before Pascal's birth in 1623. The triangle seems to have been discovered individually by the Persians and the Chinese during the 11th century. Blaise Pascal was born on June 19, 1623 in France, and he was the second oldest of four children. Blaise's mother, Antoinette Pascal, passed away when he was just a toddler, and his father was a tax collector and a talented mathematician. The Pascal family moved to Paris in 1631. Instead of going to public school, Blaise was homeschooled by his father. Ironically, his father completely omitted mathematics from Blaise's early curriculum because he assumed that Blaise would fall in love with geometry and not focus on the other subjects. He focused more on other languages like Greek and Latin. On his own, at the age of 12, Blaise started exploring geometry. He figured out himself that the sums of a triangle's angles are equal to two right angles. His father was impressed and decided to feed Blaise's fascination by permitting him to read Euclid. He also allowed Blaise to accompany him to meetings at the Mathematics Academy in Paris. There, at the age of 16, Blaise presented a lot of his early theorems. In 1640, the Pascal family moved to Rouen, France, and Blaise's father had been appointed to collect taxes. Soon after moving, Blaise published his first written book, which was entitled Essay on Conic Sections. The essay established an important leap forward in projective geometry, which involved transferring a 3D object onto a 2D field. In 1646, Blaise's father was injured in an accident, which created a shift in the whole family's religious beliefs. After the accident, a visit from a group of Jansenists led the family to convert to that belief system. During the year of the father's recovery, two Jansenist brothers watched over Blaise, which caused him to become deeply religious. In 1642, at the age of 18, his father's job of calculating taxes inspired Pascal to invent an early calculator called the Pascaline. The machines went into production in 1642, but Pascal continued to work on improving his calculator until 1645. In 1648, Pascal started writing more of his theorems on conic sections and the generation of conic sections, but his work was put on hold until 1654. Towards the end of the 1640s, Pascal experimented with how atmospheric pressure could be estimated in terms of weight. After experimenting, Pascal confirmed Evangelista's theory about the cause of barometrical variations. The triangle came to be known as Pascal's triangle, with Blaise's achievement on the treatise on the arithmetic triangle in 1654. He developed many of the triangle's properties and applications within these writings with the use of the already known array of binomial coefficients. Pascal attempted to create a perpetual motion machine which served the purpose of producing more energy than it used. In the process, he accidentally invented Pascal's roulette machine in 1655. Touching his work on the roulette machine was Pascal's communication with the mathematical theorist Pierre de Fermat in the beginning of 1654. Through their discussion, Pascal revealed that there is a fixed probability of any certain outcome when it comes to the rolling of dice. This discovery was the foundation of the mathematical theory of probability, which is the understanding that events and their outcomes do not occur randomly. Pascal also apparently invented the wristwatch. Although it was a simple version, Blaise was known to tie his pocket watch to his wrist with a piece of string for convenience, while tampering with his other inventions. Pascal suffered from insomnia and a painful digestive disorder called dyspepsia at a very young age. He lived the majority of his adult life in pain. Pascal died of a spiteful stomach tumor at his sister's house in Paris on August 19, 1662. Pascal's inventions and discoveries have been helpful to the developments in the fields of geometry, physics, and computer science. His exploration of binomial coefficients influenced Sir Isaac Newton, leading him to reveal his general binomial theorem for fractional and negative powers. In the 1970s, the Pascal unit was named after Blaise in honor of his contributions to the understanding of atmospheric pressure and how it could be estimated in terms of weight. In 1972, computer scientist Nicholas Wirth invented a computer language and insisted on naming it after Pascal. Pascal is also credited with building the foundation of probability theory. An exponent is a quantity representing the power to which a given number or expression is to be raised, usually expressed as a raised symbol beside the number or the expression. In this example, the 3 is the exponent. The exponent represents the number of times to multiply the base. In this case, your base is 2. So you will multiply the 2 3 times, and your product should be 8. A binomial is a polynomial with 2 terms, and when multiplied by itself, it demonstrates the foundation of the binomial theorem. This is an example of a binomial because it contains 2 terms. Your first term is A and your second term is B. Okay, let's say you want to multiply the A plus B by itself. It would look something like this. It's the same thing as A plus B squared. After multiplying it out, your answer should be A squared plus 2AB plus B squared. Next, we want to solve A plus B to the, can you see that? 3rd power, which is A plus B times A plus B times A plus B. Your answer should be A to the 3rd plus 3a squared b plus 3ab squared plus b to the 3rd. If you cannot tell, there was a pattern in the a plus b cubed. When looking at the a term alone, you can see that the exponents decrease with each term. You have 3, 2, if you can't see it, an understood 1, and at the end you have a to the 0, but a to the 0 is an understood 1, which is in front of the b to the 3rd. You should also be able to tell that the b's are increasing with each term. Beside the a to the 3rd is a b to the 0 power, which is an understood 1, and then it goes to b to the 1st power, b to the 2nd power, and at the end you have b to the 3rd power. A coefficient is a numerical or constant quantity placed before and multiplying the variable in an algebraic expression. For example, in this expression, your 4 is the coefficient. Coefficients also play a part in binomial equations. In this equation, there's an understood 1 right here. The 2 is a coefficient, and there's another understood 1. And in this one, there's an understood 1. Your 3 is a coefficient, your 3 is a coefficient, and there's another 1 with the b cubed. Okay, now we have a plus b to the 0 power, a plus b to the 1st, a plus b to the 2nd, 3rd, and the 4th. In the order of the equations that I gave you, these are your answers. As you can see, the length of the answers become longer as you increase, and it creates a triangle, hence Pascal's triangle. This is a demonstration of what I just showed you, but it doesn't have the terms in it, the A's and the B's. And I've also added an, a plus b to the fifth at the bottom. And as you can see that, well, there's a pattern to this too. There's your 1, and then there's your 2 understood ones, and 1 plus 1 is 2. 1 plus 2 is 3. And 3 plus 1, gosh, that is annoying. 3 plus 1 is 4. And 4 plus 6 is your 10. And, do you understand? Hard to explain. Just look at it. And I was basically trying to say that each number of the triangle is just the 2 numbers above it added together, except for the edges. The edges are all 1s. There are 10 significant properties of Pascal's triangle. The sum of the rows in any row is equal to 2 to the n when n is the number of the row. Here is an example of the sums of rows. That's a 4 at the bottom. If the first element in a row is a prime number, all the numbers in that row, excluding the ones, are divisible by it. If a diagonal of numbers of any length is selected starting at any of the ones bordering the sides of the triangle and ending on any number inside the triangle on that diagonal, the sum of the numbers inside the selection is equal to the number below the end of the selection that is not on the same diagonal itself. If a row is made into a single number by using each element as a digit of the number is equal to 11 to the nth power, where n is the number of the row the multi-digit number was taken from. The Fibonacci sequence can also be located on Pascal's triangle. The sequence can be formed by adding 2 consecutive numbers in the sequence to produce the next number. The triangular numbers can be found in the diagonal starting at row 3 as shown in the diagram. A square number is the sum of the 2 numbers in any circled area in the diagram, and they are also found in the same diagonal as the triangular numbers. Catalan numbers are found by taking polygons and finding how many ways they can be partitioned into triangles. When expanding a binomial equation, the coefficients can be found in Pascal's triangle. When all the odd numbers in Pascal's triangle are filled in and the rest are left blank, the Sierpinski triangle is revealed, showing yet another pattern in Pascal's triangle. That is all for today. Thank you for watching.